Good morning, everybody. Hopefully, everyone can hear me. My name is Karini Mendoza, and I'm the team leader of the COVID-19 surveillance system with facial recognition framework. So, to begin, let me start introducing our team members. So, I mentioned before, I'm Karini Mendoza. I'll be assisting with the hardware and software implementation of the project. We have Ahmed Jabir, who is our hardware lead, Joe Lanzi, our software lead, and they'll introduce themselves later on as they speak. Anina Bofamonte, who is part of the software team, and Brandon DeLeo, who is part of the hardware team. Now, our main motivation for our project is the impact that the coronavirus, also known as COVID-19, has on the daily norm of society. In the US alone, there are 15.2 million cases, which is the last updated from like the CDC yesterday afternoon. And because of how quickly the virus spreads, this it changes drastically daily. We were inspired to create a product that will assist with the building protocols across multiple businesses and schools that ensure the safety of others. In deciding what would be the most effective product, we considered multiple alternatives taking into account the main four criteria points, which is the cost, hardware, security, and the ease of use. When weighing our options, we decided that a security surveillance system would be the most desirable option. From this, we chose to design a product that can track building capacity, monitor the temperature of those who enter the building, incorporate a facial recognition feature that can identify like those with learning temperatures, and create a simple but multi-user interface website to monitor these features. So creating an objective tree helped us identify which requirement would be the most important, and that's starting with like the functional system design, and then being the machine learning algorithm that will be trained to identify individuals regardless of their facial coverings. And then we have the database that stores the collected data and the data for the facial recognition software. And then lastly, it will be the website, which is meant for public and public safety viewing. Let me go next slide.
Here's the marketing to engineering matrix. This is where we weighed the engineering requirements against the marketing requirements. And we concluded that the tracking and accuracy would be the two important parts to our project because they got the most double arrows in this matrix. Here's our system architecture, which shows a breakdown of our whole system and what each part is connected to. The ones that have the stars on them currently, we don't have yet, but we plan to order them and implement them for next semester. Here is the data flow diagram, which shows how our data flows throughout the system. And we have our sensors here, the data will flow towards the microcontroller, and the temperature will be displayed from the thermal imaging camera on the LCD display. And the data from the microcontroller will go to the database, and it will go to the facial recognition and to the website. And to power our system, we were thinking about using this rechargeable backup battery, but we are deciding to switch to a 5-volt wall adapter for next semester.
So in this slide, we will talk about similar research that was done in the past. Due to the ongoing pandemic, the implementation of contactless smart thermal scanning equipment, as well as facial recognition technology, is on the rise to separate people who might have the possibility to be diagnosed with COVID. Based on the table that we're seeing on the screen, most research has designed their system to measure body temperature as well as detect people who might have high temperature based on artificial intelligence and advanced thermal detection system. For example, a group of researcher NSTD from Thailand is using LiDAR to differentiate the body temperature of an individual human being in a group, and there are some drawbacks to their design too, one of them being slower processing time. Moving on to the next slide, we'll see some of the products that are already on the market. Each of these companies has both pros and cons. Some have higher accuracy when it comes to facial recognition and temperature measurement. Some can scan a large group of people at a time. Even though these products are great, they come with their own disadvantages. For example, IC2 doesn't have facial recognition at all. Aviglion cost more than its competitor. So what makes our system better? First of all, higher price to performance ratio, low power consumption, and smaller housing for the system, which will give the user access to mount on anything. And this gives us an upper hand over existing systems on the market. In the next couple of slides, we'll see some of our hardware designs for our project. On the left on the slide, we have our wiring diagram for ultrasonic sensors to determine the direction of the person, whether that person is coming in or going out of a building. These sensors have a range of 2 centimeter to 400 centimeter to sense that capability. On the right side of the slide, we have the wiring diagram for our motion sensor, which has 7 meters of sensing capability, which is more than enough to determine the presence of an individual within the vicinity of the building. On the next slide, we have our IR temperature sensor wiring on the left side, which has an accuracy on up to plus minus 0.5 degrees Celsius. In the future, we will upgrade the IR sensor to a thermal imaging sensor for better detection and accuracy. Now, on the right side of the slide, we have the diagram for the integration system or prototype. At the heart of this system, we have our MCU, microcontroller unit, which is ESP32 with onboard Wi-Fi, 34 GPIO pins, which is adequate for our different sensors, a dual-core CPU at up to 600 million instructions per second. That will help us to process the data faster coming off of different sensor. On the next slide, we will see a demo video on some of our hardware components.
This is the PIR motion sensor for the COVID-19 surveillance system. The PIR motion sensor consists of a pyroelectric sensor which generates energy when exposed to heat. This means that when a human or animal body gets in the range of the sensor, it will sense and detect movement because the human or animal body emits heat energy in form of infrared radiation. The purpose of the PIR motion sensor is to provide the system with a wake protocol when motion is detected. This is important for system redundancy when trying to detect object within the vicinity of the product. Once a person is detected, the PIR motion sensor is then used as a detection sensor to start the timing for the whole system used by the other sensors. The PIR motion sensor pseudocode consists of setting the GPIO as interrupt, starting a timer, taking an input from the motion detection, getting the current time when motion is detected, waking the system and saying that there's motion for 10 seconds, and telling the other sensors to start. As a demonstration, we can see that when the motion is detected, the red LED light is turning on, and after 10 seconds of no motion, it is then turned off.
And now we have an ultrasonic sensor, which is the HCSR04 that we'll be using. The ultrasonic emits an ultrasound of 40,000 hertz, which travels through the air, and if there is an object or obstacle on its path, it will bounce back to the module. Considering the travel time and the speed of the sound, you can calculate the distance based on how long it takes to hit the object and how long it takes to travel back to the sensor. So based on the formula, we're using the speed of sound of 343 meters per second, which then we convert to centimeters per microsecond, and we are able to find the distance. And now, as you can see from the pseudocode for the ultrasonic sensor, it transmits 8 cycle sonic burst waves per 10 microseconds. Then we measure the feedback in echo pins, and then we calculate the distance based on speed. Then the distance is equal to the time delay over 2 times the speed of sound, and then we are able to output the distance. From the video demonstration shown here, you can see that it displays a constant 100 centimeters, and that is because since there's no one walking, that will be the constant. And as soon as someone walks by, as you can see, it was the person and the dog, it changed from 100 to about 39.10 centimeters or 36.7 centimeters. And that shows that's how far the person was from the sensor.
This is one of the many unique hardware testings that we have done so far. Here's an example of the ultrasonic sensor where we tested the connection between the sensor and the ESP32, which is our choice of microcontroller. We have also tested the accuracy of the data coming off of the sensor as well. Now I'm going to hand over to Joe, who will talk about more of the software aspect of this project.
Hello, everyone. So I'm Joe Lonzi. I'm going to be handling a lot of the hardware software integration and also the machine learning prospect of the project. But starting with the software design, the product pretty much begins with a PIR motion sensor as that system wake protocol as seen in the video demo. And then once the system detects a person, it can then start recording the travel movement with the ultrasonic sensor and start that management system for the building. And then at the same time, we are going to have the thermal imaging to capture live temperature of the person and then it'll take a picture of them if it breaks a certain threshold. And then from there, we have that travel and management algorithm, and I'll be showing this later in a demo, but it'll be counting the building capacity based on the person's travel direction. And then simultaneously, we have the facial recognition, finding the person's identity to alert the security if there is a possible case. And then all this data will be backed up into the microcontroller's SD card and then updated to the database. And then all of this will be then shown to the website. And our website is pretty much composed of HTML5 as its markup language, CSS for styling. And we're also going to be using JSON-ID for automatic attachment of photos and videos, as well as encoding data respectively. And so up next, we have the remaining demonstration for the software.
The camera we will be using for our demonstration is the OV2640, but later on we will be upgrading from a 2 megapixel camera to a 5 to 8 megapixel camera, which will take up to 1,440 pixels, which is about a 2K resolution, which will be better for facial recognition. Now, as you can see from the pseudocode, the camera will configure the camera pins, start the camera from a local web server, connect to the Wi-Fi using SSID and password, then it will take the inputs from camera GPIO pins and display the frames. In this slide, you can see that the camera has been connected to the IP address of 192.168.7.103, and that is using the port of 80 and starting the stream server on port 81. From this demonstration shown in the slide, we are able to see that the web server is equipped with both facial detection and facial recognition, and it is able to be accessed through the local IP web address server, where we can see the camera viewing what's around it. So it will be able to detect, identify, and use it to send to the website. This is the home page of the website, and on the right-hand corner on the top, it says Home About Demonstrations and Public Safety, which has the databases. So the home page, which is the start page, says Greatness is Coming Soon, stay tuned. And as you scroll down, you're able to see the Leo building occupancy, and it will be shown here as well as a photo of the building. Now the location is 3825 Corlier Ave, the Bronx, New York, 10463. So that is where we will be honing in on our database, and we have a short description of what our product is. Now, scrolling back up, if you go to the About, it says how we have our innovative technology, which is our main objective, and some of the objectives that we had chosen for the project, the need for our project, as well as the advantages to why this should be built, and the equipment that was used. Lastly, we have the Meet the Team, which is all the members of the COVID-19 management system team, and all of our pictures are displayed, as well as our positions, the majors, expertise, and interests that we have. And that's what we have for now. The demonstrations page will have our demonstrations of the product being used, and the public safety page will be strictly for public safety to be able to monitor the people with high temperatures and see the capacity as well.
After integrating the ultrasonic sensor into the system, we can now create a crafty algorithm to help the system become more efficient. We can now put two ultrasonic sensors right next to each other to create our own travel direction algorithm and management system for the building capacity as seen in the picture. To quickly demonstrate how the process goes, we can see that the two ultrasonic sensors are put right next to each other and put into two different states, movement detected and movement not detected, as state 0 and 1. When a person walks through the two sensors, we can see the state of the sensor changes based on the direction of the person's travel. From this, we can create an accurate algorithm that we can then use as a building capacity counter. The travel direction pseudocode consists of everything that we saw from the ultrasonic sensor, with an addition of using that time when the system is in a wake protocol and comparing the left and the right ultrasonic trigger. If the left ultrasonic is triggered first and then the right, the system then can tell that the movement is going to the right direction, and then we can increase the count. If the right ultrasonic is triggered first and then the left, the movement is then going left, and we can say that the count is getting subtracted from the building. To quickly demonstrate, we have 3 individuals moving to the right of the building. And then afterwards, we can then see that a person exits the building, putting the total count to 2 in the building. This is the facial recognition algorithm. The facial recognition algorithm is one of the most important features of the system. While not finished, I was able to create a synthetic data that resonate a person having different face coverings. On the top left, we have an example student ID, and the rest shows possible scenario of a student's daily activity. On the bottom, synthetic images were created to account for all possible scenario and create a training dataset for the convolutional neural network. A facial detection algorithm is then used to detect a person's face and its exact coordinates within an image. If we integrate this feature with the machine learning, we can then create a regional-based convolutional neural network, which can then produce a quick and accurate pipeline in identifying a person's identity when wearing face coverings. This is the unit testing chart for the facial recognition, showing the process and completion for the algorithm, with the next step of training the model to accurately identify a person's face with up to 99% accuracy.
Good morning, everyone. My name is Anita Bolfamate. I'm the other software engineer on this project. Here we have our cost analysis, and based on the parts necessary to complete our project, we're estimating between $110 to $230. This is because of the quality of cameras we'll be using and the LCD display, as it will subject to change based on integration testing. And these are the codes and standards that we're following for the hardware and software implementations, as well as the ethical issues. So we have the TCP/IP, Wi-Fi standard, UART communication standard, and the SP standard. The ethical issues of temperature privacy, which will cause panic when visible to public. So we will implement that well. And cybersecurity, creating a website can subject to cyber attacks, where attacks can gain access to personal information stored in database, and facial recognition accuracy, which can lead to mistaken identities due to false matches. So we're ensuring that there's a 98% accuracy. And for our go, no-go milestone, our proposed milestone had the 40% of our project completed, which was the hardware parts being purchased, unit testing for both hardware and software to be completed, and the website design to be completed as well. So we have successfully been able to complete the following, which was presented above. And between the hardware and software, we have the purchase hardware, microcontroller communication, unit testing, as well as the software, web API, database, and unit testing. And below is our timeline of progression of work that was completed for our system to achieve our go, no-go milestone. And here we have the work that will be done during the winter break and spring 2021 semester. So we plan to purchase the rest of the supplies during the winter break. The facial recognition software and the unit testing will be continued. And the spring 2021 semester, we plan to complete the hardware system design, database development, web API, complete the facial recognition implementations, and the testing. And here is our future work timeline. So most of our stuff we're focusing on is finishing up the facial recognition algorithm and completing the full system integration with everything. And lastly, we're going to continue to collect data.
And here, just like the references we use to conduct research on the latest related work of our system and the related theory. And we also use like the CDC data tracker to keep track of the daily cases in the US alone. Like the last time we used it was yesterday, December 10th, and like last week it was we used it, it was about 14.2 million cases, and now we're up to like 15.2, just to show how dramatically the virus spreads, and that's why the need for our product. And then the next slide is also the references that we also used for our research. And that is all for our presentation. Thank you for listening. Does anyone have any questions?
Very good study. Okay, very nice presentation. Actually, I notice you have the reference of Van Natta. Right now, there are 50 papers from different countries and different authors, 40 to 50 papers reporting data on facial recognition using temperature. They measure the temperature remotely, One further improvement for future studies is facial recognition using for psychological effects of COVID. And because stress, depression, etc., generates fear. Fear is a component of anxiety. So people, they're trying to recognize the psychological effects of COVID to remotely. So although this does not have to do with the identification of COVID infected people, has to do with the impact of COVID to the psychological factor of these people. So keep in mind that this project can be expanded. Very good work.
Thank you. Thank you so much for your feedback.
Thank you.
Thank you.
Thank you, Dr. Yakos. Do you have any questions? Anyone has any question? Okay, thank you, all of you.